Bismillah ar-Rahman ar-Rahim. Assalamu alaikum. How are you, my dear students? I welcome you back into the online classes and hope you will all be in the best of health, wealth, and happiness. Right now, we will move on to the next chapter, that is the current electricity. Today is our lecture number first in the second spell of the online classes. Today topics are steady current, electric circuits, sources of the electric current, current direction, current through a conductor, that is the microscopic model of the current. The microscopic model of the current, and the most important, the drift velocity, right, which is the main theme of our lecture. So let us start with the name of Allah Almighty. Bismillah ar-Rahman ar-Rahim. The first one is the steady current. Now, in the previous chapter, we studied charges at rest, right? And that was charges what? At rest. And that was which part of the electricity? That was the static electricity. Static electricity. And if you remember there, I told you that electricity has two main branches: static electricity, the study of charges at rest, and current electricity, that is the study of charges when the charges are in motion. So today we are actually studying the current electricity. So what is the steady current? The steady current is in fact the continuous flow of charges. What? It is the continuous, it is the continuous flow of charges. It is the continuous flow of charges that is called the steady current. Steady current is also, we can define this as the rate. Physically, we can define it as the rate of flow of charges, rate of flow of charges. That current is in fact what? It is the rate of flow of charges, delta Q by delta T. Right? Now, you see that here the charges, current can be constitute even if a single charge moves. It is not necessary whether the charge is moving in a metallic conductor like copper wire, whether the charges are in motion like in a fluid, just liquid like electrolyte, even in gases or like plasma. Okay, so even if there is a single electron or bunch of electron, but if they move, they will constitute what? They will constitute the electric current. Right now, there are two important aspects which I will discuss. Whether if the charges are what? Whether if the charges are electron, right, or whether they are proton. Normally, in a conductor, this is not possible because they are fixed at their position. Whether even if they are ions, right, the positive charge ion, the negative charge ion, for example, anion and cation. So when they move, they will constitute an electric current, just like an electrolyte, or you can take the example of the battery. Then there are also charges can be, it is because of what? It can be because of the holes are the vacant site, and inshallah we will discuss which consider to be just like a positive charge carrier, and we will discuss this in a semiconductor chapters, but it is related to the semiconductors, and they resembles to like a positive charge carrier. And why I use the word resemble rather than a actual, inshallah I will remember once when I reach there, then I will explain it to you. So whether the charge is positive or whether the charges are what, whether the charges are negative, they will constitute the electric current. Now, for the electric current to happens, there are two most important point. One, you have the that is the free electrons or charges. Free electrons, since we are usually studying in this chapter the metallic conductors only, so I use the word free electron. So the free electrons are important here. And second, the potential difference. The potential difference. These are the two important points. Not alone the free electrons enough. There must be a potential difference also across the ends of the conductor to provide a steady current. So these two are the important aspects, and I will discuss them one by one. The next point here is the electric circuit, some special terms for the electric circuits. So I will be back to this inshallah very soon, but I just want to tell you some few specific things regarding the electric circuits. That is, what is the electric circuit? The electric circuit is it is in fact the electric circuit. Electric circuit is nothing but the path of the current. The path of what? The path of the current. That is called the electric circuit. So any conducting path through which the current can flow is called the electric circuit. We have two kind of the electric circuits. There is one we call the open circuit. The open circuit. Now, what is the open circuit? The open circuit is the one in which the path of the current is what? In which the path of the current is incomplete. And we have one, the closed circuit. The closed circuit. So let us first tell you about the open circuit. For example, let us consider if we have a bulb, and like bulb, this is just I will make, oh this is too big. For example, if we have this bulb in a circuit, and let us we just connect this is a switch, this is the positive terminal of the battery, this is the negative terminal of the battery, and you see that this is the open circuit. And open circuit is the one in which the path of the current is incomplete, so that constitutes the open circuit, right? So here you see the switch is open, so the circuit is called the open circuit. Why? Because there is no current flowing in the circuit. Now when you close the switch, the path of the current is complete. The battery pump charges or drive electrons around the circuit as you see, and as a result which the bulb convert your electrical energy into light energy. We call this circuit as the this circuit is now termed as the closed circuit, right? So we have the closed circuit also. Clear? Now another important thing here is the circuit components, right? That is also important. The circuit components, component of the electric circuit. Sorry, components of the components of the circuit. Now, what are the component of the circuits? That is, the circuit must have some source, input source. You have the input source in your circuit. That is sometime we call the EMF source. Later on, we will discuss the EMF in great detail. For example, look, we have the resistor. Later on, I will explain what is resistor also, which should have got this thing, which is resistor, which allow the constant flow of current in a circuit. We have various type of resistors. We will discuss them also. We have the capacitors, right? And we have the diodes and etc. There are many electrical components. For the EMF source, we have the batteries. Batteries are usually denoted by one long bar and one short bar. The AC source there might be the AC source also, which is denoted by waveform. There are current measuring instruments also, which we can sometimes install in the circuit. That might be the galvanometer, right? And it might be the ammeter. We will denote the ammeter by this symbol. And the resistor, sorry, I did not show that. We have the resistor by this symbol, and the variable resistor by this symbol. This is the variable resistor. So the capacitor, two vertical bar of the same length, that is the capacitor. We have the variable capacitor. So the variable capacitor can be denoted by drawing the arrow above it. We have the diodes. The diodes have electronic symbol like that. The galvanometer, the ammeter, the voltmeter, like this. So these are all called the electrical component, right? So let move on to the next topic. And some of the electrical component I may miss out here, but down the road, whenever uh, uh, these becomes the part of our study or lecture, then I will explain instantly to you, inshallah. So these are all about the electrical components of the circuit. So main story is that we have two kind of electric circuits: the open circuit in which the path is incomplete, and the closed circuit which the path is complete, right? Then there comes the sources of the current. So there are various sources of the current. For example, we have the cell, and you know that cell is one basic unit of electricity, and you have learned this in class 10, that cell convert chemical energy into the electrical energies. And then we have the battery also, and you know that battery consists of two or more cells together to provide greater current or voltage source. So then second, we have the secondary cells also, and the primary cells also. Primary cells are once used, we can dispose of, and secondary cell, they can be recharged. And beside the cells, we have the generators also. And generators in fact converts the mechanical energy into the electrical energy. So we have the generators also. And similarly, we have the solar cells also. Solar cells which convert which convert the solar energy into electrical energy. And we have the thermocouples also. Thermocouple, and I think this will be the part of your scheme of study also. So thermocouples actually converts heat into electrical energy. So we will discuss the thermocouples also. Okay, so these are our sources of current, because they if we don't have any input source, then there will be no electric current constituted, and we will discuss this thing here. Now, there are, let us come back to our topic, this about the steady current. As I told you, that few things are important. One, free electrons, right? Electrons, rather a free charge is better. But since we are studying metallic conductor here, so this is why I say free electrons, right? So one is this thing. The second is the potential difference, and I will come to this topic also about the potential difference. The potential difference. I will discuss this with you also. Okay. But let me tell you that what is the SI unit of what? The SI unit of the current. Current is usually measured in the SI is SI unit. SI unit is ampere. It is measured in ampere, and 1 ampere of current is equal 1 coulomb of charge is 1 coulomb per unit time. So if 1 coulomb of charge flows across the cross-sectional area of the conductor in 1 second, then we will call it 1 ampere of current. Since 1 coulomb of charge is a very huge quantity of charge. If you remember, I told you that 1 coulomb of charge will be constituted when 6.25 into 10 raised to the power 18 electrons there. So the charge on these many electrons can constitute 1 coulomb. So it is usually very larger unit, and then we can use the milliampere unit also and the microampere also, right? The second important point that usually until now we consider current as the scalar quantity, and of course it is a scalar because charge is a scalar quantity and time is a scalar quantity. But in order to simplify circuit calculation, so we need to assign the steady current a direction. So direction of the current is also important, and we will now explain what really we means current direction, right? But let me, I will come to this later on, but first I just want to explain this thing to you, the flow of the free electron. You see, the as I told you, that current is the flow of what? The flow of charges, and in metal, it is usually the free electrons, right? Which constitutes the current. But normally, you see that we do not feel such effect in a conductor. Why? Because you know that when you pick a conductor like is the one here which I shown, see here, normally you have what? Lock, you have the free electron as you see, and the motion of these free electron is all random in a conductor. So the number of free electrons moving to the right is the same as the number of free electron moving to the left. So the net free motion of the electron is zero, and this is why we say that there is no net electric current through the conductor which has length L and which has area of cross section A. So normally when they are not connected to any electrical supply, then we don't have any electric current through the conductor because of the random motion of the free electrons. Though the conductor have free electrons, but we do not have any electric current across its ends. Why? Because there is no potential difference. Now, even if you connect the two ends of the conductor, the end A and the end B of the conductor, then still directly through a wire, through a metallic wire, still we cannot accept what any, sorry, still we do not have any current. Why? Because the electric field inside the conductor is still zero. Why it is zero? Because every point inside the conductor is at the same potential. So there is no potential difference across the end A and B of the conductor or the end X and Y of the conductor. So we do not expect no current. So this is what I actually wanted to show you the two things needed, the free electrons and the potential difference. Both are important. If you do not have the free electrons like an insulator, so even when you connect it to the across the ends of across the battery, you cannot imagine any current in the circuit. But if you have the free electron, but if you don't have the potential difference, still there will be no current. So the net current due to the motion of the electrons in a conductor, though in a conductor the electrons freely move, but they do not constitute a current because of the absence of what? Because of the absence of the potential difference, right? They, since there is no potential difference, the electrons moving to the right the same as the number of electron moving to the left, the net effect is zero. Now let us comes to let us comes to what? Let us comes to the main part of the topic, and that is the current direction. The current direction, as I told you, current is a scalar quantity, but in electrodynamics we consider current as a vector, a kind of, right? We need direction for the current to simplify circuit calculation, to calculate for the current and other major physical quantities. There are two kinds of current: the conventional current. The conventional current is if the direction of the current is taken from the positive terminal of the battery towards the negative terminal of the battery, we call it a conventional current. How? For example, let us see that if we just connect this conductor, let us consider, for example, the conductor like this one. For example, if you connect this end with the positive terminal of the battery and the other end with a negative terminal of the battery, okay, and now the path of the current is complete and you have provided a potential difference, the x end of the conductor and the y end of the conductor. The x end of the conductor is at a higher potential, let's say VA, and this is at a lower potential, C is VB. This is low potential and this is what? The high potential. Since potential differences created are provided, then the current will begins to flow in a circuit, right? This will cause a steady flow of current and the electron will now flow in the circuit. Now the electron may flow, the current direction may be taken from the positive towards the negative or from the negative towards the positive. In both aspects I'm going to explain. One, we call this the electronic current direction. The electronic current direction, that is when the current direction is taken from the negative terminal of the battery towards the positive terminal of the battery. Then we call this the electronic current direction. Let us do the first one. This current direction, the conventional current direction, this is called conventional because you know that it is very much related to a traditional way. Why? Because let me explain to you that the current conventional current direction is that you see that look inside, it was before the discovery of the electron, when electron was not discovered and when the electrical effect was discovered. So you know that in a batteries there are electrolytes. So in batteries this current is due to the movement of the anion and cation, both mean the positive charges and the negative charges. So usually we prefer positive aspects of the thing. So at that time, the engineers and the scientists thought that let the direction of the current can be taken from the positive electrodes towards the negative electrodes. But later on, when electron was discovered, then the engineers and the scientists, they came to the conclusion that, oh, these are the free electrons in a conductor which move. These are not the positive charges, because you know the positive charges like proton, they are what? They are fixed in a conductor, as you see. For example, If I just denote this as the atoms, these are the atoms, for example, you know that atoms are what? Atoms are fixed at their position inside the conductor, right? They do not move, right? So means the proton inside there is a nucleus. Nucleus contain a positive charge, so the nucleus does not move. So we cannot say that positive charge in the metal constitute a current, right? Once the electric field is established across the conductor after providing the potential difference, as you see, look here, in this case you have what? The electric field, and the electric field is from the positive terminal of the, that is from the positive end of the bit to the negative. This is uniform electric field which is established inside the conductor. So the atoms are fixed at their position, the positive charges do not move, and we have what? And we have the free electrons, and those free electrons are in fact the charge carrier. As you see inside the conductor, the free electrons tends to move in a direction opposite to the direction of the electric field, like this, like this, like this. Okay, and they are the current carrier. Okay, so this is why that in fact the current direction should be taken from the negative terminal of the, instead of the positive terminal of the battery, they should be taken from what? They before, in the conventional we are doing this, but in what? In the, oh, I'm so sorry, but in the non-conventional or in the electronic current direction, they will be taken from the negative terminal of the battery towards the positive terminal. Both are correct. The question is why? Because as long as it does not in conflict with the physical changes of the physical quantities, then okay, we can accept. Why? Because that it doesn't make any sense whether the electron moves clockwise, whether the charges move clockwise or anti-clockwise, they will produce the same heating effect, right? And what we are why we are considering the conventional current in our book? Because for the conventional current direction, though the current is due to the motion of the free electron in a conductor, but we choose the conventional current direction throughout in this book, because here we replace equal number of negative charges by equal number of positive charges. Why? Because because the charge on electron is the same as the charge on the proton, right? So this is why it does not produce any contradiction or anything conflicting. This is why we say okay, fine, we will stick to whatever our elders have chosen. So this is why we usually use the conventional current direction. So conventional current direction, when the current direction is taken from positive towards the negative terminal of the battery. In electronic current direction or the actual current direction, this is actual also. So in metallic conductor, if it is taken from negative to positive, usually most American books follow this one, but no problem, calculation will remain the same. Is it clear? Now let us comes to the next topic, that is the current through a conductor, microscopic model of the current. And this is what I already explained to you, that in a conductor, free electrons are what? The free electrons are the current carrier. Free electrons are what? Are the current carrier. The current carrier. And this is because of the velocity of the electron, or this is because of the effect called the effect, that is the drift velocity, which I will explain to you shortly. The drift velocity Vd. Now let us consider of a conductor. You see that we have what? We have the conductor. In the previous case, you have seen that in a conductor, there was, even when you connect them without any potential difference or potential source, the electric field inside is zero. Why? Because every point is on the same potential, right? And the motion of the electrons are found to be random. Now when we connect the one end of the conductor with the positive terminal of the battery, and the other end with a negative terminal of the battery. this time the positive and the negative end is at the VB is at high potential and VA is at low potential, and this is what the high potential, right? So there will establish an electric field, and the electric field inside this will be like this. It is the direction of the electric field is shown here. This is the direction of the electric field, right? Here the actual current direction is shown, right? But conventionally that it will be just like this. The current will flow from what? The current will now flow from like what? It will be in this direction. Yes, this will be the direction of the current, and the conventional current direction I. Okay, so now let us see that, as I told you, that look, what is the current? As I told you, that current is the rate of flow of charges through a cross-sectional area, as I marked A, right? It is because of the velocity called the drift velocity. Drift velocity is the velocity of the free electrons under the influence of external electric field E. So when the electron moves under the influence of its external electric field E, then the velocity of the electron is termed as the drift velocity. Right now, let us do some calculation. Let's see that how much charge can flow across the conductor. For example, let us consider the volume of the conductor, the total charge. If we have n electrons, and if we have the n number of electrons, right, and that is these electrons contain the n number of electrons, the length of the conductor, that is the in the volume of the conductor we have these much electrons, right? And L is the length of the conductor, and A is what? A is the area. A is what? A is the area, and such that each conductor carry a charge E, that is the charge on electrons. So these are the total number of electrons that is that can pass through the cross-sectional area of the conductor in time, in unit time t. So let's rewrite this equation as n e l a through the unit area of cross section of the conductor n time delta t. But you know that what is velocity? If the electron starts from the end A, that is delta x, this is actually the length which the electrons cover. You see that, look, what is velocity? This drift velocity. The distance covered by the electron per unit time delta t. Right? We can write it like this. The length of the length of what? The length of the distance that is traveled by the electron, right? So what is this length? It will be Vd into delta t. So you just put this equation that n into E into what is this L? This L is the V drift, right? Into the V drift into delta T into A into delta T. And you see this will get cancelled, and what is left with you? And that is the N E into Vt into A. So two things here the most important, that current is directly proportional to the area of cross section. So a thick conductor may have more current than a thin conductor, and I is directly proportional to the V drift. And you must know these things because there are questions, but this is not directly included in the calculations, or the expressions are not the part of your scheme directly. that current increases with increase in drift velocity, with increase in drift velocity, right? And this drift velocity, how does it increase? Increases by increasing potential difference, increases by increasing the potential difference, the potential difference. So current always depends on the drift velocity of the free electron. Greater the drift velocity, greater will be the electron, right? So drift velocity is in fact what? The velocity of free electrons in groups under the influence under the influence of external electric field, external electric field. So this is our today lecture. Most in our today lecture, you have studied about the steady current, you have studied about the component of the electric circuit, you have studied about the current direction, and more importantly, you have learned about the drift velocity, right? That drift velocity is actually the cause of the current in a conductor, in a metallic conductor. And you have learned that drift velocity is only available when the conductor is connected with the external potential difference source, right? So inshallah, see you in the next lecture, and in the next lecture we will study about the Ohm law.